Thank you very much, Marcello, and good morning to everybody. I'm pleased to start this second session today, which is the second part of this very successful event. We had a very great rate of participation in the first session, which was held the day before yesterday. Before starting, I just want to emphasize once more, which is the purpose of this event. We want to share with you the main concept of the project, but especially the methodologies that we are carrying out within Impress, which have the scope to advance further the innovation in the field of transmission electron microscopy applied to as many as possible scientific domains. As we said before, it is important to focus the main asset of the Impress project. Actually, as you may already know, we are now facing the middle phase of our journey in Impress, and I think many of you already know that Impress stands for Interoperable Electron Microscopy Platform for Advanced Research and Services. Impress is a funded project within Horizon Europe in a specific funding scheme, Horizon Research and Innovation Actions, and an Infratech call, a call that was awarding proposals capable to deliver research and development for the next generation of scientific instrumentation tools and methods. What this mean for us when we started to write our project? As electron microscopists, we had to start from a really careful analysis on the state of the art on electron microscopy. If you just have a brief look at the roadmap which has developed over the last century, electron microscopy has faced many developments. You can see here many corner milestones. One of the latest one of electron phytography, but there are many others. This is just to say that at the heart of these developments, there were important innovation developments. But now the main question is how to progress further. In this respect, we have to say that TM in general is facing a major bottlenecks because it is recognized that TM equipments are often large, costly, and expensive to maintain. In many cases, they are focused on very specialized applications, which brings a major return to the individual laboratories, but a scarce return in terms of applications for wide user communities. And this is mainly due to the fact that there is a restricted flexibility of the instrumentation to customize the experiments. So the main question remains how to move towards a new TM area. And this question was for us that we were called to write this project. It is, of course, clear that there is a need of a disruptive technological step change at the TM facilities, which means that the TMs have to be able to cross scientific domains and expand more and more their field of applications. This means that TM infrastructure have to be open to offer flexible combination of techniques into fully interoperable experimental arrangements. Please note that here interoperability is a key word, but it doesn't apply only to open data, data sharing and data handling, but also to hardware components, and especially to the need for standardized and interconnected methodologies. In this framework, open innovation and co-creation are keywords, and they are at the basis of a reinforced dialogue that we have to establish and to promote between companies and electron microscopy experts, because this is the only way to overcome the monopoly imposed by the big manufacturers and the technical challenges that cannot be solved nowadays by the electron microscopy market alone. This means that scientists, companies have to be ready to co-develop, to co-design new prototypes in order to provide the user communities with optimal and flexible services to perform innovative experiments. In one word, in one sentence, we have all cooperate to make TMs flexible to a diversity of multimodal experiments instead of adapting experiments to TMs. With this in mind, we developed Impress. Well, the core of the project is indeed the co-development of an interoperable platform consisting of interchangeable hardware and software components which are based on a modular and standardized cartridge within cartridge concept. We named this concept ECAT, where E stands for electron, CAT for correlative, adaptable, and transferable. Correlative because this cartridge has to be designed in such a way to allow any user to design a correlative experiment, ideally from the bench, to bringing to TMs, to many TMs from different manufacturers, and also to expand it to other instrumentation. The cartridge has to be adaptable in order to be adapted to the requirements of the users and to be further implemented over time depending on user needs. The cartridge has to be transferable in order to move interchangeably between the different planes of an electron microscope across different TM instrumentation and also across different instrumentation. This is exemplified by this sketch, which put the cartridge, the schematic of the cartridge at the center of the scheme, where all the instruments are cross-correlated to each other, so the cartridge can physically go from the electron microscope to many other characterization techniques, including synchrotron techniques. Here you can better see which is the concept, the schematic concept of the cartridge. Indeed, here you can see a cartoon, a schematic of the cartridge, which includes in its core all the possible and suitable stimuli that you may think you can apply to an electron, to a sample suitable for electron microscopy characterization. The sample is put here, and you can see that the cartridge is designed from the very beginning with all the possible biasing, going from electrical contact, cooling, heating, liquid and gas environment. But what is important to underline is that thanks to this modular concept, the cartridge will be adapted in order to span across the different planes of the electron microscope, so it can interchangeably go within the across the objective planes, the diffraction plane of the electron microscope, and thanks to the support of a rod within rod concept, can physically span across different instruments and different other characterization techniques. Of course, this has been realized, and we are cooperating in this direction, having together 19 strategic partners across the European landscape. And they are very well diversified because they are distributed within strategic countries, and they are spanning across research and performing organizations, university, and five research infrastructures. So this is very important to underline, because the research infrastructures are those that connect Impress with users, with the wide community of users. Then we have 3 small and medium-sized enterprises which are already into the game and involved as co-developers and co-designers together with the scientists, but more and more will join the consortium in the next month. This is the structure of the project. You can see the scheme here, which recalls slightly the geometry of an electron microscope. So there will be, in this interconnected structure, we will span across work packages dedicated to electron sources with enhanced beam properties and electron optical performance. This was afforded the day before yesterday in the first session of the workshop. workshop, as well as the focus on optics and detectors for advanced imaging and spectroscopy. Then we have a work package dedicated to in situ operando and correlative methodologies, which, as I said, is the core of the session of today. All this, which is mostly devoted to hardware development, is interfaced with a work package dedicated to software, remote control, automation, and development of artificial intelligence methodologies, which, of course, is cross-talking with all the work packages and was afforded in the first session of the workshop. The important thing is that all these work packages are interconnected with the building block, the main backbone of the project, which is the work package number 2, which is indeed devoted to the development of interoperable platform and of all the technological prototypes that will be developed at the end of the project. As I said, the core today will be to get more into the contents of the in situ operando and correlative methodologies, which is the core of work package number 5. And this is led by Vittorio Morandi at CNR. And the work package is broken into 5 main task activities, which are devoted to the development of novel electrochemical cells and microreactors for operando experiments for battery research, microreactor for correlative photocatalysis, a task devoted to cryo and bio applications. And this is very important for us because although the main focus of Impresa is devoted to material science applications, we also span to another domain to show the value of interoperability and the value of multidisciplinarity of our technologies. Then there is a task dedicated to correlative spectroscopy and Riggs and Deals applications at synchrotron beamlines, and then another one dedicated to ultra-fast transformations in materials. The important thing that I want to stress is that for each of these tasks, we target research infrastructures. As I said before, this is to develop workflow case studies in direct cooperation with users. And that's why the session of today is extremely important also to transfer to you as an audience the outcome of the developments that we are putting into play together. So I conclude my presentation again with this rapid overview on the agenda of today. And of course, I wish to thank you for your attention.